See if I can read more. How's everybody doing? Good. Doing great. Okay. You guys will be pleased to hear that now I got the whole Zoom thing fixed. So we're not going to be like getting kicked out anymore and having to re-enter. Yeah, got that fixed. In terms of how to watch previous classes, you can go to my YouTube channel, find that there. But I soon will be able to adjust it to where you can find it on Canvas as well. All right. Yes. Okay, so we're going to be going over hopefully all these sections if we can, but we'll start with 5.1. Okay, has to do with quadratic equations. Okay. Quadratic equation. Quadratic equation is a function f of x is equal to ax squared plus bx plus c. Okay, where a, b, and c are the coefficients in front of that you see there. Okay, and we can graph quadratic equations, but there is a standard form of a quadratic equation. That's when we have our f of x equal to some a times x minus h squared plus your k. That's when we get our quadratic equation, which represents a parabola, to have vertex at h, k. Here's our point h comma k. So when we write it in standard form, that's what we have here. The center, the region in which the parabola has its vertex is apparent in the standard form equation. What do we mean by that? We mean that let's see here, that if we had a parabola and right here it had a vertex at 2, 3, then we know that this has a function f of x is equal to some a times x minus 2 squared plus 3. We don't know what a is, but we could possibly solve for it. Okay, how to be able to solve for this a is, let's say if we knew what the y-intercept was. Let's say this is the point 4, right? That, bringing the mathematics over here, would mean that f of 0 outputs a 4, okay? But that is also equal to our unknown capital A multiplied times our, it was x, but now it's 0 minus 2 squared plus 3, right? So now what's inside here just becomes a 4, a positive 4. So then we get 4 is equal to 4a plus 3. We can algebraically solve this equation by subtracting a 3 from both sides. So I get 1 is equal to 4a, right? And then I can divide both sides by 4, and I get a is equal to 1/4. So then the equation here then becomes f of x is equal to 1/4 x minus 2 squared plus 3. And so we know it. Also, given something in the quadratic form versus the standard form, we can attain the standard form. It would just require us to factor, right? So for instance, all right, let's say we have something in, let's say we have 2x squared plus 4x minus 8 is equal to our f of x, right? What if I want it in standard form? What is it in standard form, right? What we can do is we can set our equation f of x equal to 0, right? That would mean that it's equal to 2x squared plus our 4x minus 8 is equal to 0, right? So what I can do is I can add an 8 to both sides, and I would get 8 is equal to 2x squared plus 4x, right? Notice that now I can factor out a 2, so I get x squared plus 2x times 2 is equal to our positive 8. So this implies, if I bring the computation up here, if I divide both sides by 2, divide by 2, divide by 2, I get 4 is equal to x squared plus 2x. But I want it to look like this. I want it to look like in standard form. That's when my f of x is equal to some a times my x minus h squared plus k, because then I know where my parabola has its vertex at. It's at this h comma k. Okay, so I want to get this to be factored. So that means what I'm going to do is I'm going to complete the square in variable x. I get my b, I divide it by 2, and I square it. And for those of you who need more help with complete the square, check out my YouTube channel. I'll type it in here. It has many videos on college algebra stuff and calculus and trigonometry, stuff like that. I have around 1,400 subscribers, and I would appreciate your subscription and likes and whatnot, whatever. Anyways, this becomes 1 squared, which becomes a 1. So I add that to both sides. If this doesn't make sense, you need to look at that video about completing the square. But we've already talked about completing the square in here. But that gives me 5 over here, and this becomes x plus 1 quantity squared is equal to our 5. So notice that I can subtract this from both sides, and I get 0 is equal to my x plus 1 quantity squared minus a 5. All right, and notice that this equals 0, and we had set our function equal to 0 originally, right? So that means our function is equal to this. And so this is exactly the same thing as this. But we have it in a standard form. And now we can find out where is this parabola centered at. Well, its vertex is at a -1 and -5 right here. If I find -1, I find -5, I put a dot. Okay. Then we have to determine whether the parabola is opening up or down. And clearly it's opening up because it has a positive number out here, not a negative. But where does it touch here? What is this point? And where does it touch here? And where does it touch here? Question mark, question mark, question mark. Let's find that out. All right. So let's start off with this y-intercept. At the y-intercept, the value for x is 0. So I can find the y-intercept by setting all x's equal to 0 in this equation. So then that becomes 0 plus 1 quantity squared minus 5. Okay. What is the output? That's our y. Y is set equal to 0. It's really our f of x, right? It's our f of 0, which is our y-intercept. So then this becomes 1 minus a 5, which becomes a negative 4. Aha! So this point is at negative 4. What about the x-intercepts? There should be 2 of them. If we have a parabola, there should be 2 of them. So here we set x equal to 0 to find the y-intercept. Now we set y equal to 0 to find the x-intercepts. Okay? So then 0 is then equal to this x plus 1 quantity squared minus a 5. All right, so I add a 5 to both sides. And I get this x plus 1 quantity squared here. Then I take the square root of both sides. So I get the square root of 5, plus or minus technically, is equal to x plus 1. Right? And then I subtract the 1 from both sides. So I get x is then equal to negative 1 plus or minus the square root of 5. These are the 2 x-intercepts. One of them is negative 1 minus square root of 5, right here. And this one is negative 1 plus the square root of 5, right here. Any questions so far? Okay. So then, what if I were to just give you a parabola? What if I were to give you an image? I gave you the algebraic equation, and you were able to generate the image. What if I was giving you the image or the graph, and I asked you to compute the algebraic expression, or to determine it? Well, let's do so. Let's have a parabola opening down. Okay. And let's say that this is at 3, 1, 3, 1. All right. And let's say that one of the intercepts is at 2, one of the intercepts is at 4, and this intercept is at negative 2. All right. What is the graph? What is the equation for the graph? What is the equation for the graph? Well, we know that in standard form, f of x is equal to some a times our x minus h quantity squared plus k. So then we have to determine, okay, what is h and what is k? Well, this is our h comma k. And so I replace h with 3. And k with 1. So we get our f of x is equal to this. But what is a? We don't know what a is yet. That is to be determined. I don't know what a is yet. So this is our f of x. But we can't just leave it like that. We want to find what is the explicit equation. So we can't have an arbitrary a here. We need to determine what a is. So how do we do that? Well, we can say, well, f of 2 is 0. Because the function is equal to 0 at 2. I could have even said f of 4 is equal to 0. Doesn't matter. But then that means when I replace every x with a 2, I get this. But then this is equal to a times a negative 1 squared, which becomes a positive 1 plus 1. So this is a plus 1. So a plus 1 is actually equal to 0. That's what we get. So this implies that a is equal to negative 1. So that means I can rewrite my equation like so. Do you guys see how beautiful that is? Notice how beautiful that is. Because now we get that minus sign here, and it respects the fact that the parabola is opening down instead of up. The mathematics just works itself out to just being right like that. Isn't that amazing? When math is so beautiful and everything works like clockwork. Now, you should have gotten the same equation if I said, that what is f of 2 was 4. You should get the same thing. All right. Who here has heard of how to solve what's going on here? Oh yeah, let's talk about here a general form of quadratic, and then how do we find its center? So, okay, so given a quadratic function, ax squared plus bx plus c is our f of x. Okay. How do we find an hk? Meaning, find the standard form in general. What's the general form that when we start here, I know exactly how I can find my h and my k without graphical information, just algebraic information? And that requires some calculus. You say, well, in general, if I have a parabola, that the slope of the tangent line, oh my goodness, that's a terrible tangent line. It's a terrible parabola. Undo it all. We have a parabola. Okay, we say, where is the slope of the tangent line? When is it equal to 0? That's equivalent to knowing when is d dx of f of x evaluating to 0. So we take the differential operator of ax squared plus bx plus c, and we set it equal to 0. So when we take that derivative, we get 2ax plus b is equal to 0, and we solve for x. So we get 2ax is equal to negative b, and I get x is equal to negative b over 2a. And so when I plug it back into the function, negative b over 2a is our h, and our k will then equal the function evaluated at negative b over 2a. So this is how you can convert from your arbitrary quadratic function equation to a standard form quadratic equation. This will be your h and this will be your k. Meaning in general, ax squared plus bx plus c is equal to our f of x is the same thing as some a times x minus is the same thing as some a times x minus r negative b over 2a squared plus r negative b over 2a evaluated by the function. Did everybody understand this part? No, not yet. You understand it? Well, then you must have some pre-existing knowledge if you understand that. For a pre-calc 1 class like this, we have not, it's called pre-calc, meaning before calc, meaning before calculus. So this is a calculus thing. So you don't have to know how to do this. You don't have to know how to do any of that. All you need to know is that your h is some negative b over 2a, and your k is f of negative b over 2a. What do I mean by that? Good. I hated calc. No, don't say that. If I was your calculus teacher, you would not hate it. What does this mean? Well, recall our previous utilized example. I gave you some f of x that equaled a 2x squared plus a 4x plus 8. Or was it a, yeah. I think it was a minus 8. Yeah, it was a minus 8. Okay, so we had this, and we did all that work to find h and k. We got some values for that, but we can find h and k just taking negative b over 2a. This is one of our h's over here. So this is actually vh. There's just not one. This is vh. So we get this negative. We can put a negative 4 over 2 times a 2. And I get this is negative 4 divided by 4, which is a negative 1. This is our h. Okay. Then we get f of negative b over 2a, which is the same thing as f of negative 1, which is the same thing as our function having everything replacing a negative 1 when you see an x. Okay, so then that becomes a 2 minus a 4 minus an 8. Comes to negative 10. So this is where our k is. So we know that our parabola will be centered or have its vertex at negative 1, negative 10, like so. Now, whether it opens up or down depends on the number out here. So, and we know it's going to open up like this. Let's do another problem. Let's say our function f of x is equal to 3x squared minus 7x plus 5. Find the vertex of this parabola. Again, its vertex is located at hk, which is the same thing as a negative b over 2a, comma, f of negative b over 2a. All right, so our b is negative 7, our a is a 3, and our c is a 5. So notice that then this breaks down to negative 7, which is 7, divided by 2 times a, which is 2 times 3, which is going to become a 6, minus our f of negative 7, which is positive 7 over 2 times 3, which is 6. All right. Notice that this becomes 7 over 6, comma, f of 7 over 6. So what is f of 7 over 6? Well, that's when I replace every x with a 7 over 6. Square it. So this becomes 3 times 49 over 36 minus 49 over 6 plus 5. Okay. So this then bringing this calculation over here, I get 3 times 7 times 7 divided by 6 times 6, which is 3 times 2 times 6. I can cancel out 3's here. And so then that means I get that term to be 49 over 12 minus 49 over 6 plus 5. To establish a common denominator to add these fractions, I multiply top and bottom here by 2. And so I get this is 49 over 12 minus doubling 49 gives me 98 over 12 plus 5. Now they have a common denominator. So it's 49 minus 98 all over 12 plus 5. Okay. So then that's the same thing as a negative 51 over 12 plus 5. Isn't that right? Because when I add 49 to that gives me a 90. No, I think that should be a 41. Because when I add 49, I get, no, that's what's going on here. Just doing the calculation here. If I can get a scientific calculator over here. Okay. So, okay, actually this becomes negative 49 all over 12 plus 5. So then that's 7 times 7 with a negative on it, all over 2 times 6 plus a 5. So to establish a common denominator, I multiply top and bottom by 12 over there, so I get negative 49 plus 60 all over 12. And so the difference between the numerator additions is, if that was a, okay, so it's 11. So this is our k. So now I know our h, and now we know our k. So the vertex is at 7 over 6, comma, 11 over 12. So these kinds of problems kind of are cool because sometimes they can model real life situations. So we already did that. So let's invent a problem. Okay. Let's say let's say you're on 100. Let's say you're on a 112-foot high cliff. You're up here and you throw a rock. Okay? Notice that the trajectory of the falling rock will create a parabola. We're interested in knowing if the rock is thrown, let's say, at a speed of 96 feet per second. The equation of motion of the rock for its height with respect to time is negative 16t squared plus 96t plus 112. What we aspire to know is, what is this distance right here? Meaning, if you're on a 112-foot high cliff, at what time does the rock hit the ground? So this is a distance. I wrote t, but what I want to really know is, at what time t does the rock hit the ground? How do we solve that? Well, we say that, okay, this axis is the h of t axis. It's the height. This axis is the t axis, which is the time. Okay. So what is the height when it strikes the ground versus what is the height when it's up here? Clearly, its original height at t equals 0 is the height of the cliff. And that makes sense because h of 0 then equals negative 16 times 0 squared plus 96 times 0 plus 1112, which is equal to 1112 because this is 0 and that is 0. So the original height is 112 feet. And that makes sense because right when you threw the rock, you're on top of a cliff of 112 feet in height. So what we want to know is, how long will it take if you throw it at 96 feet per second? What's the time t which it takes for it to strike the ground? Well, what you have to do is you have to set the height equal to 0 and solve for the corresponding time. Right? So now we are solving a quadratic equation. And there's many ways to do that. And one of them is the quadratic function, or the quadratic equation, and that's t is equal to negative b plus or minus the square root of your b squared minus 4 times your a times your c all over 2a. Okay. What do we get here when we do this equation? Do some calculations here. Okay, so what's inside here becomes a negative 4. whenever you compute it. So our equation then, we get t is equal to -96 plus or minus a -4 all over. Oh, well, all over part was incorporated in the -4. So this is going to be over -32. But then I believe that can go into it. So let's get that as well. That becomes a -3. So it reduces to -3 plus or minus -4 is our t. So we'll get two values, one of which will not make any sense and another one which will make sense. What is t minus? That's when we elect to subtract. We get -7 seconds. That doesn't make sense. You can't have negative time. What happens when we add? We would get -3. Well, this was t plus. The above was t plus when we decided to add. When we decide to subtract, this is when we get a real answer. Minus a -4. And we all know why a minus times a minus is positive. So this becomes +1. So it becomes 1 second. And you can have positive time, so we take this to be our answer. So the time it takes for the rock to hit the ground is 1 full second, according to our calculations. Moving on to the next section. (5.2). Power functions and polynomial functions. So here's what a power function is. It's a function f of x. It's equal to some a x raised to some power p, where a is a constant. So let's talk about the end behavior of power functions. Okay. So let's say p is even. So then we have our function f of x is equal to, a x to the p. For example, we have x squared, x to the 4, x to the 6, x to the 12, x to the 22nd, x to the 100. All of these are even power functions. And maybe I can put a number out here in front, 4, 7, -12, pi. They're all power functions. And their end behavior is that they kind of look like our parabola, all right? Various forms of them look like parabolas. And what happens is that the limit as x approaches infinity of our function f of x, it becomes infinite. Meaning, the more and more I go towards the right, the higher and higher this function gets. So if I go infinitely to the right, the function goes infinitely up. Similarly, the limit as x approaches negative infinity of our f of x, that equals a negative infinity. Positive infinity again, I mean, it equals positive infinity because the more and more left we go, the higher and higher the function gets again. So the limit as our x approaches negative infinity, meaning we go on the x-axis to the left, our function approaches positive infinity, meaning our function blows up in value and gets higher and higher and higher. So that's the end behavior of even power functions. What is the end behavior of odd power functions? What about p is odd? Okay. Well, then, here's some examples. X cubed, 14x to the 17, negative pi squared x to the 15. All right. What do the graphs look like? Graphs look like this. In general, odd power graphs look like that. So, in the limit, as x approaches positive infinity, okay, of f of x, it tends towards positive infinity. Because as I go farther and farther on the x positively, the function grows towards positive infinity in the y. So we'll get that. What about the limit as f of x for x approaches negative infinity? Well, that actually equals negative infinity this time. Because as I go to the left, our function drops dramatically down towards negative infinity. So that's the end behavior of an odd power function. So for example, describe the end behavior of x is equal to x to the fourth. Well, we're able to do this because we know it's even and that the limit as x approaches positive infinity of our f of x is the same thing as the limit as x approaches positive infinity of x to the fourth, which is positive infinity because the function values always grow. On the other hand, the limit as x approaches negative infinity of our x to the fourth is still positive infinity because the function grows whether you input positive values into take them to the fourth power, or whether you put in negative powers and you take them to the fourth power. Any even power will cause a negative value to become a positive value, like squaring it, or taking it to the fourth, or taking it to the 100th. So what about our function g of x is equal to negative x to the 7th? What's the end behavior of this guy? Well, the limit as x approaches negative infinity of our g of x is the same thing as the limit as x approaches negative infinity of negative x to the 7th. But notice, this is the negative of an input of negative raised to the odd power. So the output is a negative number. And when you negative a negative, it becomes a positive. So this becomes a positive infinity. So the end behavior, when you go to the left horizontally of f of x is equal to negative x to the 7th, is that it grows towards the positive vertical. Now, what is the limit as x approaches positive infinity of negative x to the 7th? Well, I'm inputting positive numbers, and you raise them to an odd power, which is still positive, and you tack that negative sign on it, so it becomes negative infinity. So when you go to the right, the function drops down towards the bottom. That's how you do end behavior for even and odd powers. Now let's talk about polynomial equations. Okay. How about we have an equation a n x to the n plus a n minus 1 x to the n minus 1 plus a to the a1 to the x to the 1 plus a naught. Let's say this is our f of x. This is called an nth degree polynomial. Our nth degree polynomial means that the largest number in this chain is n, so it has degree n. For example, let's say I have 3x to the 4th minus 15x plus 12x squared minus x to the 100 minus x to the 14 plus 5 is equal to my f of x. What is the degree of this polynomial? The degree is the highest power that you see in the chain. So we go and we look, and oh, maybe this guy, 100. All right. And so the leading coefficient here is an being the leading coefficient. So the leading coefficient here will be -1. Because that's the value out in front of the highest degree polynomial term. Given another polynomial, What is the degree? Well, the degree is power, 3. And what is the leading coefficient? Well, that's the number out in front of there, which is 14. Any questions so far? So now let's use what we've learned so far and apply it to polynomials. Meaning, let's discuss end behavior. Negative 3x squared is x minus 1 is x plus 4. Okay. What is the end behavior of this guy? And what is its degree? Well, we asked about its degree because that is actually important in determining what is the end behavior. So the end behavior is dictated by the leading power, which is the degree. So if the degree is even, that means it's going to have even end behavior. And if the degree is odd, that means it's going to have odd end behavior. Okay? So let's determine the degree here. You can already tell that the degree is 4. But let's assume we don't see that immediately. Then what you got to do is FOIL or distribute. I like to call it distribute. What happens when you do that? We get an x squared plus a 4x minus an x minus a 4. What happens here? I get a negative 3x squared times a x squared plus a 3x minus a 4. What happens here? Then we get a negative 3x to the 4th minus a 9x to the 3rd plus a 12x squared. That's why we realize the degree is 4, because this was a quadratic term being multiplied by the product of two binomials that have polynomial degree 1, degree 1, degree 1, degree 2. Add those numbers up, we get a degree 4. So that's why we get a 4 here. We could have seen it right off the bat. And we notice that the leading coefficient has a negative sign. So this is an even power function. an even degree power function, meaning its end behavior will be dictated by its even value. So the limit as x approaches infinity of your function, it will rise, and get that negative sign on it, so it becomes negative infinity. And the limit as x approaches negative infinity of our function, again, the negative gets raised to a even power, making it no longer negative, but it gets multiplied by a negative, so it becomes a negative. Here, the positive remained positive until it got the negative on it on the outside. Here, the negative became positive, and then it got the negative out on the outside again. So this function tends towards negative infinity in the end behavior of going towards the left or to the right horizontally. Give me 1 second. One moment. All right. My apologies. I had some family issues to address. Okay, moving on. All right, now let's determine intercepts. Okay, we already did some of this before with the parabolas, but let's do another one with a product of binomials. So let's say, what is the intercepts of x minus 1, x plus 1, or x minus 1, x plus 2 times, what am I doing? This should be minus 2, and this should be plus 1. Minus 4. So determine the intercepts of this function. So we don't even know what the function looks like when we graph it. I, right off the bat, know that it's a cubic function, because when we multiply these out, the highest degree we'll get is a 3. Okay? We're supposed to know, when does this touch the x-axis? And, you know, it's equivalent to discovering what the roots of this equation is. So we set this equal to 0. Why are they called roots? Well, it's because that's where it's touching the ground, if you will. That's how I think about it. That's what I believe they mean by roots. Okay? To find the roots, you set each of the factors in the product equal to 0. Because logically, that is all possible. So this implies I get x is equal to 2. This implies I get x is equal to negative 1. This implies I get x is equal to positive 4. Okay? So that means the positions are at negative 1, positive 2, and at positive 4. These are where the roots of the function are. This is where the function will be going through the x-axis. Now, what we need to determine is what is the end behavior of the function. Okay? Clearly, it's a cubic function, right? And clearly, the leading coefficient will be a 1. You could do that by foiling twice or distributing twice. And we'll notice that this is a cubic function, meaning the limit as x approaches negative infinity, the values will keep getting lower and lower and lower. So you go like that. So the function then must go above and turn to go down here, because it can't go forever. It must then go through the root, as we've discovered there. Furthermore, then we know if it's going to go through that root, it can't go down here forever either. So it must eventually turn and go back up, just like a cubic function would. We would assume that a cubic function would do that, because for higher and higher positive values, the cubic function will output higher and higher positive values when we input it. Don't believe me that this is a cubic function? Well, I'll show you that it is. We'll FOIL it. So this becomes x minus 2 times what is inside here. This becomes a x squared minus a 4x plus an x minus a 4. What does this become? Then this becomes x minus 2 quantity times x squared. Group those like terms to get a negative 3x minus a 4. All right. So then this becomes x cubed minus 3x squared minus 4x minus 2x squared plus 6x plus 8. Regrouping like terms, I get that this equals x cubed. Let's regroup these two terms here. I get negative 5x squared. Then let's group these terms right here. So I get a positive 2x. And then I put this plus 8 here. And again, voila. We see that our function is a cubic function with a positive leading coefficient, as we hypothesized. One thing that we have neglected to do, though, is to determine what is this y-intercept. We've discovered the x-intercept because those are the roots, and we solve for the roots. Now we got to find what is that y-intercept. The y-intercept is when x is equal to 0. So we set all the x is equal to 0 in this function here. All right? Notice that that outputs a positive 8. Zero, zero, zero. The only thing that remains is that positive 8. So over here, this is at the point 0, positive 8. Any questions? So the last thing we'll cover in this section is trying to go in the opposite direction. We were given the algebraic expression. We were supposed to determine what is the graph look like and the end behavior. Now, what if we're given what the graph looks like and the end behavior, and we're expected to determine information about the algebraic structure? Let's say you're given a graph like this. All right. And let's say this point, and this point is given by some weird values here. All right. So it's like in between -3 and -2. This is then in between 2 and 3. And this y-intercept is exactly identically at a -2. All right. What can we say about a function that has end behavior like this? Clearly, the limit as x approaches positive infinity, function goes up. So it goes to infinity. And clearly, the limit as x approaches negative infinity, function goes up. So it approaches positive infinity. So then that means that the function has odd degree. Limit as x approaches positive infinity, the function equaling positive infinity, and the limits as x approaches negative infinity of the function outputting another positive infinity. This implies even degree polynomial. Notice how many times it crosses the x-axis? Twice. So that implies, yes, it's even, and the degree is equal to 2. Notice then also that it has some turning points here. Turning point here, turning point here, turning point here. This suggests that it doesn't necessarily equal a degree 2 polynomial, even though it is still an even degree polynomial. Meaning, it's got to be an even degree polynomial that's not necessarily second degree. So it's going to be degree equaling 4 or above. That's due to the fact that these turning points show that there must be more sign changes in the output of the function. Okay. So now you know when you have turning points, they change the root value of what you might have assumed they would be. Okay, so keep that in mind. If you assume that it only crosses the x-axis twice, that it has only a degree 2, that's not necessarily true. But then it still had to retain the fact that it was an even degree polynomial because it was exhibiting this kind of behavior. So that means that it had to be 4 or higher. And we're done with that section, so we're on to 5.4. Now we talk about dividing polynomials. Okay. So let us talk about polynomial long division. Let's take 2x cubed minus 3x squared plus 4x plus 5. And let's divide this by x plus 2. How do we pull this off? Well, what you do is you put the denominator, what people tend to call outside the house. I don't know why that's a thing, but fine. And then you put the numerator inside the house. I don't know why people call it that, but whatever. It's just a notational tool towards figuring out what these values are when we compute them. Whatever you want to call it, that's fine. Here we're going to start the division algorithm. the division algorithm. What does that say? It says step 1, take your highest degree polynomial term, x, over here, and take the highest degree polynomial term here, this 2x cubed, all right? And what you do is you're going to say, I want my 2x cubed, and I want to divide it by x. What do I get? All right, that's step 1. And we notice that we get a 2x squared. And so we put that, what people like to say, on top of the roof. Whatever you want to call it, that's fine. Let me move this over a little bit. It's getting in the way. All right, so you grab this, you put it on top of the roof, if you will. Step number 2, you get that term and you multiply it times what's outside the house. And then when we send that through, we get 2x cubed plus 4x squared. All right, 2x cubed plus 4x squared. And we write that here. And we draw what we call a subtraction bar. All right. What I like to do is, instead of having a subtraction bar, I like to change it to an addition bar. And I distribute a negative throughout these terms. Then we notice that these terms cancel out. And we notice that these terms add up to a negative 7x squared. And we bring the rest of the terms plus a 4x plus a 5. All right. And we can just forget about this 0 now. Then we repeat the division algorithm all over again. So we get that 2. So now what we do is we get the highest term polynomial here, divide it by that again. So repeat. We get that negative 7x squared divided by that x. Compute what we get, that's negative 7x. We place that on top of the roof. So it's a negative 7x. All right. Then the second step in the algorithm is we get our negative 7x and multiply it times what's outside that x plus 2. Notice that then we get a 7x squared minus 14x. That's what goes here. And then we put our subtraction bar. What I like to do is convert the subtraction bar into an addition bar and distribute a negative through each term. Then these terms cancel. I get a 0. And these terms add up to a positive 18x. And we bring down that 5 here. So we can forget about this stuff right here. Then we repeat the algorithm once again. We get that leading term, that 18x, divided by the leading term out there. So we get an 18. We grab this 18. We put it up here. And I put plus because it's a positive. Then we get that 18 and we multiply it through what's outside. It becomes 18x plus 36. So that comes right here, 18x plus 36. And I put my subtraction bar. And I like to turn the subtraction bar into an addition bar by distributing a negative. Notice that then these two cancel and I get a 0 here. And then I get, this is a minus 29. Oh, what am I doing here? No, that's a minus 31. So we can forget about this here. Then we repeat the algorithm and we notice something funny happens. I get that minus 31, I divide it by x. Nothing happens. I can't divide x into the minus 31. It just can't happen, it doesn't work. So this is where we terminate the algorithm, meaning we stop. The algorithm stops because the division can't continue. What happens then is our quotient, our 2x cubed minus 3x squared plus a 4x plus a 5 all over x plus 2 is then equivalent to what's on top of that roof, partially, that 2x squared minus a 7x plus an 18, and we got to add the remainder here. This negative 31 all over what was out here, x plus 2. Why am I doing this weird stuff here? Well, think about it. What is 7 divided by 3? 7 divided by 3. Oh, well, that goes into 7 twice. But then there's a remainder, right? What's the remainder? 3 can go into 7 twice, and what's the remainder? It's a 1. And so the remainder is 1, meaning what we put here is a 1/3. 2 and a third is how many times 3 can go into 7? 2 plus 1/3. So notice that over here, this is behaving like that x plus 2. And that's why you see it in 2 regions divided by the divisor. So polynomial division and number division are very related because polynomials are truly generalized numbers. Any questions so far? It's nice that we don't keep getting cut off. I'm allowed to kind of get some momentum here. Each time we get cut off, we kind of cut the momentum. This begs us to discover a generalization of polynomial division. Notice if I get a function, f of x, being the ratio of some g of x over h of x, that means f of x is equal to some divisor times a quotient plus a remainder. Well, what does this even mean? Let's go back to, let's say, 4 over 3. All right. We know that's 1 plus a third, right? Well, multiply both sides of this equation by 3, and we notice that we get 4 is equal to 3 times this 1 plus a fourth. Or I mean a third. Which means I get 3 times 1 plus 1. Where 3 is like the dividend, the divisor, 3. Q is the quotient, meaning what do we get without the remainder when we divide? 1. And R is the remainder, is what do we get when we do divide and we get the remainder. Let's do more examples. Let's get 5x squared plus 3x minus 2. And divide it by x plus 1. We know that means this x plus 1 comes out here. This 5x squared plus 3x minus 2 comes out here. And now we begin the algorithm. Step 1, get this leading value, 5x squared, divided by the leading value here, compute the results. It's 5x. Get to that, place it on top of the roof. Step 2 of the algorithm is get that value, 5x. Multiply it times what's on the outside, that x plus 1. Notice that this ends up giving me 5x squared plus 5x. We then bring that over here and we create a subtraction bar. This 5x squared plus 5x. Then we distribute the subtraction bar. We distribute the negatives and we create an addition bar. Notice that this and that cancel to get me a 0. And we regroup the like terms here to get me a negative 2x minus a 2. So we can kind of forget about this 0 here. And then we repeat the algorithm. You get this minus 2x. We divide it by the leading term on the outside. Give me this negative 2. Get that negative 2. Put it over here. Second step of the algorithm, we multiply by the negative 2 times the product of the outside. So this becomes a negative 2x minus a 2. We write that here with a subtraction bar. We turn the subtraction bar into an addition bar by distributing the negatives. Then we group. So this plus itself is 0, and this plus itself is 0. And whenever you get this kind of situation, the algorithm terminates on its own because there's nothing else to do. If we try and then do the algorithm, we get 0 divided by our x, which is just 0. Okay, and if we put 0 on top of the roof and then multiply times 0, then we get 0, and then we add 0, we get 0. So it's meaningless to pursue the algorithm any further in this case as well. So all of this points towards this being equivalent to, oh, I erased it. What was on top of the roof? Yeah, 5x minus 2. So that's how we get polynomial long division. There is another method of dividing, and that's called synthetic division. But synthetic division only occurs when you have a linear term here. What does a linear term mean? It means degree 1. So here we could have used synthetic division, and synthetic division is much easier than polynomial long division. But if in any case this is no longer a linear term, it becomes quadratic, synthetic division doesn't work anymore. So long division always works, whereas synthetic division only works when the degree of what's in the denominator polynomial is 1. So I don't even consider synthetic division as an option. I only care about polynomial long division, because if you have polynomial long division, you can do every case, whereas synthetic division is a limited method. So why don't we do one where a divisor is not something that synthetic division can do? Let's divide a 4th degree polynomial by a 3rd degree polynomial. Let's say x to the 4th minus 3x cubed plus 2x squared minus 1. Let's divide this by x squared plus 1, x squared plus x plus 1. All right. What does this equal? Well, we have to put what's on the denominator outside here. And what goes inside the house is the numerator. X cubed plus 2x squared minus 1. Step 1 of the algorithm. Get what's the highest degree on the inside of the house. Divide it by the highest degree on the outside of the house. Compute the result, which is x squared. Get that result and put it on top of the roof. Step 2 of the algorithm. Get what's on top of the roof and multiply on outside. Multiply times what's on outside the house. the result is a x to the fourth plus a x cubed plus a x squared, x to the fourth, x cubed, x squared, and we put a division, and we put a subtraction bar here, right? And then we can create that subtraction bar. We can cause it to become an addition bar by flipping the sign of each of these. All right. Then regroup. Now we add. So these cancel. And we can regroup these to become a negative 4x cubed. And then regroup these to just become an x squared. All right. And then regroup this to just become a minus 1. Okay. Then we repeat the algorithm. Step 1, get what the highest value degree term here, divided by what's on the outside, x squared. What do we get here? This becomes a negative 4x, right? Negative 4x. We grab that, we put it on what's on top. We put it on top of the house, negative 4x. Step 2 of the algorithm. We get this negative 4x and we multiply it times what's on the outside of the house. This ends up becoming a negative 4x cubed minus a 4x squared minus a 4x. So we reproduce that here, negative 4x cubed minus a 4x squared minus a 4x. And we put a subtraction bar. We then convert the subtraction bar to an addition bar by flipping the sign of each of these. And then we add. So these cancel because they're the same thing. This becomes a positive 5x squared. Then this becomes a positive 4x minus 1. Then we redo the algorithm. Step 1, get what's the largest term here, 5x squared, divided by the largest term out here, x squared. What do we get? We get a 5. Grab that, put it on top of the house. Step 2 of the algorithm. 5 multiplied by what's on the outside here. This ends up becoming 5x squared plus 5x plus 5. So we reproduce that right here. 5x squared plus 5x plus 5. Put a subtraction bar. Create an addition bar by distributing a negative. Regroup like terms, so this becomes 0, so they cancel. This becomes a negative 4x. This becomes a negative x here. And this becomes a minus 6. All right. So then we redo the algorithm. Step 1, get the highest term here, negative x, divided by the highest term there, x squared. What do we get? A negative 1 over x. Can't continue because the algorithm must terminate because this doesn't divide through evenly. So we stop here with our remainder being negative x minus 6, meaning we get as what you'd intuitively think would happen. The division of a 4th degree with a 2nd degree gives me a 2nd degree polynomial. X squared minus 4x plus 5 plus this is negative x minus a 6 divided by x squared plus x plus 1. So that is the result of the polynomial long division in this case as well. Any questions so far? So there's no questions. Moving on to the next section, 5.5. Zeros of polynomials. Also known as the roots. Okay. So first we must discuss the remainder theorem. The remainder theorem. It says that if a function f of x is divisible by some x minus k term, that implies that the remainder is f of k. So that's what the remainder theorem says. Let's apply it to find zeros of polynomials. Okay? So let's say we got our f of x is equal to 6x to the fourth minus x cubed minus 15x squared plus 2x minus 7. want to use the remainder theorem to evaluate at x equals 2. So evaluating it at x equals 2 means that the function is divisible by x minus 2. Okay? But first we have to find what the remainder is. So the remainder theorem says that if this function is divisible by x minus 2, that implies the remainder r is equal to f of 2. I can plug in f of 2 and figure out what that is into the polynomial. We realize that that's equal to 25. F of 2 is equal to 6 times 2 to the 4th minus 2 cubed minus 15 times 2 squared plus 2 times 2 minus a 7. All right. This is 6 times 16 minus an 8 minus this becomes a 4, so this becomes 60 plus 4 minus a 7. Okay. Believe it or not, this breaks down to being equal to 25. So the fact that f of 2 equals 25 implies that this function is divisible by x minus 2. That is what the remainder theorem tells us. That the function is divisible by x minus 2. And once you divide it through, what is the remainder is actually the value f of 2, which is 25. It'll have a remainder of 25. Now let's talk about the factor theorem. The factor theorem says k a 0 of f of x if and only if and only if x minus k is a factor of f of x. Meaning if you could show x minus k is a factor of f of x, then that means k is a 0 of f of x. This is quite simple to show. If f of x is equal to some g of x times some x minus k, then x minus k times g of x equals f of x, meaning x minus k is a factor of f of x, meaning if we were to set f of x equal to 0, then this would imply that not only is g of x equal to 0, but also x minus k is equal to 0, which would imply that when we solve, we get x is equal to k, and hence why k is a 0 of f of x. So why don't we use the factor theorem to find the zeros of a polynomial function? Let's show that x plus 2 is a factor of x cubed minus 6x squared minus x plus 30. What did the factor theorem say? It said, again, k is a root of f of x if and only if x minus k is a factor of f of x. So we have to show x plus 2 is a factor of this. Well, this means that our k is negative 2. Right? Because x minus k, in this case, if k is negative 2, then I get x minus negative 2, which reproduces that x plus 2 over there. So k must be a minus 2. Now, notice that x plus 2 is a factor of f of x. Here's f of x. Implies that k is a root of f of x. Meaning, if we can evaluate f of negative 2 and it spits out a 0, then we're done. We've shown that it's a factor of x cubed minus 6x squared minus x plus 30. So let's do it. This is negative 2 cubed minus 6 times the negative 2 squared minus a negative 2 plus a 30. This becomes a negative 8. This becomes a negative 6 times a positive 4. This becomes a positive 2. And this becomes still our 30. then this becomes a -8 minus 24 plus 2 plus 30. Okay? When you combine these two together, you get a -22. And then when you combine -22 with -8, you get -30. And when you -30 with +30, you get 0. Done. So by the factor theorem, we have shown that x plus 2 is a factor of this. Now let's talk about the rational roots theorem. The rational roots theorem. It says that given a polynomial, an nth degree polynomial, given some nth degree polynomial with integer coefficients, then every rational zero of f of x of the form p over q. So the theorem implies that every rational root of f of x of the form p over q, where p and q are integers of lowest form, meaning most simplified, where p is a factor of the constant term. And q is a factor of the leading coefficient. That is what the rational roots theorem states. So let us utilize the rational roots theorem to list all possible zeros of a function. let's say our function f of x is equal to 2x to the fourth minus 5x cubed plus x squared minus 4. What we want to do is list all possible rational roots. So they're all going to be able to form P over Q, where P is a factor of the constant term and Q is a factor of the leading coefficient. So P is related to the factors of the constant term. The constant term is a -4. What are all the factors of -4? Well, -4 is equal to -2 times 2. It's also equal to -4 times 1. So all the factors are plus or minus 4, plus or minus 2, plus or minus 1. Moving on to Q. Q relates to the leading coefficient, 2. What are all the possible factors of 2? Plus or minus 2 and plus or minus 1. Okay? So the way we can list all the possible factors, the way we can list all the possible rational roots for this polynomial function is we take all possible combinations of P over Q. So the way to do it is fix P and go through Q. So here's the list. Fix at plus or minus 4 and go through these. Then there's plus or minus 2. This breaks down to plus or minus 2. Then there's plus or minus 4 divided by plus or minus 1, which is the same thing as plus or minus 4. So here's one of them. Here's one of them. Okay. So we're done with 4 plus or minus 4. Now let's go to plus or minus 2. Plus or minus 2 divided by plus or minus 2. It's the same thing as plus or minus 1. This is another one of the list. And plus or minus 2 divided by plus or minus 1. This is the same thing as plus or minus 2. Oh, but that's a redundant one. We already had that on the list. And then now let's go to plus or minus 1 divided by plus or minus 2. This gives me plus or minus 1/2. That's a new value on the list. And I'll get plus or minus 1 divided by plus or minus 1. This is the same thing as plus or minus 1. So the list of non-repeated roots is, here's our list. Plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 1/2. Let's do another example. remember P over Q, where P correlates to the constant term factors, and Q correlates to the leading term factors. So what about 2x cubed plus x squared minus 4x plus 1. List all the rational roots. List all possible rational roots. P correlates to all the factors of the constant term, which is 1. For 1, all of its factors are plus or minus 1. Done. What about Q? Q correlates to all the possible factors of the leading coefficient, which is the number 2. And all the possible factors of 2 is plus or minus 1 and plus or minus 2. So P over Q is all the possibilities. So here's our list. We fix 1 divided by plus or minus 2. So this gives me plus or minus a half. This is one of them. Then we fix plus or minus 1 all over plus or minus 1, which gives me plus or minus 1. Here's the other one. So there's only 2 possibilities. Okay. Next, we talk about the fundamental theorem of algebra. The fundamental theorem of algebra. It states that an nth degree polynomial over the complex numbers has n roots. But we don't do complex number stuff in this class. So it says, for our purposes, that an nth degree polynomial has at most n roots. So something like f of x is equal to x to the 17th plus 14x squared. This guy has at most 17 possible roots. Over the complex numbers, it has all 17 roots. But if we did exist over the complex numbers, the fundamental theorem of algebra states that f of x can be broken down to x minus c1 times x minus c2 times x minus cn, where is equal to 0, where c1, c2, cn are complex numbers. They're complex roots. So let's apply both the fundamental theorem of algebra and the rational roots theorem. Let's say we have a function f of x is equal to 3x cubed plus 9x squared plus x plus 3. All right. And let's say we want to find the roots of what this function is equal to. All right. Using the rational roots theorem, we know P over Q, where P correlates to the constant term and Q correlates to the leading coefficient. To find the list of the possible rational roots, what we got to do is find the factors of the constant and the leading coefficient. For P, it's the constant, so it's 3. And so it's plus or minus 1 and plus or minus 3. Similarly, the leading coefficient 3, it's plus or minus 3 and plus or minus 1. So P over Q is plus or minus 3 over plus or minus 3, which is equal to plus or minus 1. This is one of them. It's plus or minus 3 all over plus or minus 1, which is equal to plus or minus 3. And then it's plus or minus 1 all over plus or minus 1, which is equal to plus or minus 1. And it's plus or minus 1 all over plus or minus 3, which is equal to plus or minus 1 over 3. So we have 1, 2, 3 distinct possible rational roots. So let's check. This is a list of the possible. Possible. It doesn't mean that they're all rational roots. Some of these are not even rational roots at all, but they're the possible ones. So let's check which ones work. Notice there's 1, 2, 3, and we got to double them. So it's 6 because the plus or minus for each of them gives you another distinct one. Okay. You can start checking and checking and checking. And what you'll end up realizing is that one of the roots is a f of negative 3. That's 3 times negative 3 cubed plus 9 times a negative 3 squared plus a negative 3 plus a 3. These cancel. This becomes a 3 times a negative 27. This becomes a 9 times a negative 9, positive 9. And so this becomes a 81. 3 times negative 27, negative 81. What's going on here? That f of negative 3. Negative 3 squared is 9. 9 times 9 is 81. 3 cubed, negative 3 cubed is negative 27. Negative 27 times 3, 6. Okay. So we notice that this equals 0. So f of -3 is one of the roots. Okay. Then this is what the rational roots theorem got us. Rational roots theorem got us that that -3 is a root by the rational roots theorem, the RRT. There's another theorem that can come to play here to allow us to find the complex value roots, and that's the factor theorem. That says, oh, if f of -3 is a root, then x minus -3 divides f of x, and f of okay. So what does that mean? That means our f of x is equal to 3x cubed plus 9x squared plus x minus 3 divided by x plus 3 gives us something meaningful. Okay? What ends up happening is when you do polynomial long division, you end up getting that the numerator, this is equal to x plus 3 times 3x squared plus 1. All right. So what we wanted to do was find the complex roots and the rational roots. So when we set this equal to 0, we got x plus 3 is equal to 0, and 3x squared plus 1 is equal to 0. This piece got us that x is equal to -3, and we already knew that. This piece is what's going to give us the new information about the complex roots. And that'll be the last thing we do today. I subtract a 1 from both sides, and I get 3x squared is equal to -1. I divide by 3, I get x squared is equal to -1/3. And then I take the square root of both sides, and I get x is equal to plus or minus the square root of -13, 1/3, I mean. And so this means that x is equal to plus or minus I root 1/3. Which, you know, that's the same thing as plus or minus I 1/√3, which is the same thing as plus or minus I, when you rationalize the denominator, √3/3, which is equal to your x. So you get two answers. You get 3 roots for the 3rd degree polynomial, which is what you would expect utilizing the fundamental theorem of algebra. One of the roots is x equals -3. One of the roots is when we add, it's equal to positive I √3/3. And x minus is when we subtract, and that's -I square root of 3/3. These are our 3 roots over the complex field. And by doing that, we've effectively gone over 5.5. There's one last thing. It's called René Descartes' rule of signs, and we can talk about that next class period. Is there any questions? All right. See you guys next week then.